It's really great to be here. First of all, I would like to really thank Monica and Ricardo for organizing these things. It's a really great pleasure for me to be here in person. Yes, for those who are online, you don't see all the happy faces here, which are covered by masks, but still. So the course was supposed to take place last year, and then because of COVID it got postponed, but in fact it has been useful for me to learn a little bit more about the subject, because it is really vast. I guess I heard it from Polyakov that if you have to prepare for your lectures, you're not ready to give them. But I still have to prepare for the lectures, and I definitely feel that there is much more to be understood. But I hope I will not bore you too much, and I hope it will be useful for some of you, because I think really it's a really incredibly beautiful subject, and moreover, I mean, it's relatively old, because one of the first paper on the subject was, I guess, in the 40s, and it was a golden period in the 50s and the 60s. But in the last few years, there has been a great resurrection, or a new life, sort of, for the subject in particular. Even if you looked at, on arXiv, I think yesterday there was another paper which touches the point with which I would like maybe to start. So the subject of the lecture is the S-matrix theory, and well, the S-matrix theory is, as I said, it was born in the 40s as a tool to think about relativistic quantum theories. And the basic idea is that if we have a relativistic quantum field theory, and let me avoid some subtleties, but in this setup, the physical question we would like to ask is the following. We have some in-state consists of many particles, and we have the outgoing states consist of many particles, and all the physics, all the scattering processes encoded in the transition amplitudes. And the idea was this is the fundamental object that we have to study, and all the space-time, all the physics that we know of is emergent from this question. So in this sense, it's the S-matrix approach is, I guess these days we can call it holographic, in the sense that it's really anchored at infinity. So then I thought, because we have some time, so I can spend some time talking about it, but also because the subject is old, I would like to say a few words about my take on it, and from the standpoint from which I like to talk about it, because it's an old subject and there are many points of view, there are many approaches. Probably people would disagree on some things, but to be clear, let me just say what I find interesting and what is important, etc. So the basic point upon which everything is based in the subject is the following: that if we have, say, a quantum mechanical theory, a non-relativistic quantum mechanics, and you ask like, what is the theory of particle interaction, you can formulate maybe this question as like, what is the potential between the particles? And then in principle you can write whatever potential you want. That's it. However, if you try to now make the theory relativistic, and here's where the miracle happens, when you take the theory both quantum mechanical and relativistic, and this refers, by this I will try to be, 1 year ago I prepared something, and I mostly thought about massive theories, But now during the last year, there was really a lot of beautiful work on the gravitational scattering, so I just dropped it and also forgot all proofs which I prepared for last year for the massive. So I will not distinguish sharply. So both for massives S matrices and for the gravitational S matrices, when you consider a theory to be relativistic and quantum mechanical, there is a certain rigidity that appears. We can call it bootstrappiness, which is that suddenly, if you try to combine the basic principles, you take just the basic principles together, you find that it's very hard to satisfy them. Well, in other words, it's not even clear a priori that these principles are self-consistent. For example, it's not obvious that if we introduce these axioms that there is a solution, and for the quantum field theory, we believe that it's true because, well, we have Lagrangian, we have experiments. So this is the reason why we believe it's true. For gravitational theories, it's less clear, and this is what I guess you heard the talks by Andrea about flat space holography. It's a question, okay, what is the set of axioms, and are they even consistent, etc. For gravitational theories, because we do not have Lagrangian and do not have experiment, clearly we don't know it. But in any case, so this rigidity and bootstrappiness is the key to the whole subject, that we will find a set of basic principles, and to satisfy them will be hard. Now, the subject was really, there was a lot of amazing work on it done in the 60s. And in the notes, I collected some of the literature. There is some of the classic books. You can take a look. Some of them are not an easy read, and I think partially the reason for that is that there is a famous book, The Analytic as Metrics, and if you try to read it, you should really read it like a stream of consciousness, because it doesn't end anywhere. If you try to read, okay, so where do we start? What is the punchline? You will not be able to make sense of it, because there is no punchline there. But in fact, there is a lot of amazing stuff. And so in the 60s, people, and yes, and I collected some of these books in the notes, you will see them, but in the 60s, people did a lot of work, and they were really excited. They discovered there is this bootstrappiness, and so, okay, let's now solve QCD, just based on general principles. So even there was some radical people there, like Jeffrey Chu, who would say, like, okay, let's just solve everything. Everything just follows from the fact that it makes sense. And this was a bit too fast. So, and sometimes, usually, you can often hear that S matrix bootstrap has failed in the 60s. So, well, one thing I think it definitely failed is it failed to communicate its successes. That's for sure, because there is a lot of amazing work, and it's completely forgotten. And it's like archaeology. If you work on the subject, you think, oh, I discovered something amazing, and then you just find this paper with 0 citations, which did exactly that in '66. So you should always keep this in mind. But okay, when we say that the S matrix failed, or usually what is meant, one thing that meant is that they couldn't answer two questions, two basic questions. So what is this squeaking normal, or? So what is a complete set, or well, complete or not complete? Let me put it in brackets. Set of sort of basic principles. In other words, what are the axioms? Okay, I will talk about it, and then we can discuss and argue, etc., etc. And more importantly, how to systematically go from basic principles to interesting and reliable physical predictions. So they couldn't answer two of these questions, and in other words, say they were trying to solve QCD. Okay, they were deriving some set of rules, and the set of rules got more complicated. Then they were trying to apply it QCD, coming up with approximation schemes. Like there is this strip model or strip approximation which was used, and say again, you can find it in the notes. Say Weinberg, I think, wrote about this strip approximation whose mention will bring tears to the eyes of those of us who are old enough to remember it. So okay, no one is crying here, so I assume you all forgot. So anyhow, this is what they couldn't do. Now, this was done in the 60s, and then but the outcome of these explorations were, of course, famously string theory, and then discovery of QCD. And okay, this was such exciting subjects and so successful that this program was a bit abandoned. Now, why do we want to say talk about it now, or why I think it's really exciting and worth revisiting it? Well, let me mention a few of the developments that happened since the 60s. And of course, there are many developments, but I will mention just few that are relevant to us. Well, first of all, we really had a revolution in perturbative methods. Well, they were the way that people do the perturbative computations these days, and it's very rich, it's thriving, there are many new ideas and many new results. On the other hand, and of course, this is this perturbative methods and computation of Feynman diagrams, there is nothing wrong about it. It's great, it's very useful, and for LHCs, that's probably what if you want to do prediction for LHC, what you usually do. However, in this course, I will not be talking about Feynman diagrams, because the idea would be to try to answer. So the key word here is that we are talking about non-perturbative properties. Now, still, it will be useful. Maybe some of these methods will be useful. So far, there was no much. I would say so all these old ideas, non-perturbative ideas people developed. If you combine them with new perturbative methods, well, there is no much more that you can say. But I will comment on this more. Finally, let me comment on something that we had. We had the discovery of ADS-CFT. And we have, say, a really amazing tool that was developed, which is a conformal bootstrap. Now, to put this in perspective, I think it's fair to say that 2 and 3 is completely just a very practical, concrete realization of this program. So what Mandelstam and Shu dreamed about what to do for the S matrix, I think 2 and 3 is doing just this. So ADS-CFT answers question 1, and it answers it like this, that if you want to, say, consider scattering in ADS, say gravitational theory, then you should just accept a set of CFT axioms. That answers completely question 1. And then how to do systematically computations? Well, that's conformal bootstrap allows you to do. You just take your set of axioms and you start deriving rigorous bounds. Of course, I'm not saying that now we solved everything, but it's just these two tools are incredibly powerful, and they are exactly answering the questions that people were trying to answer for the S matrix. So I think this is This is great. So in a sense, this program was just, they started in the north. The questions were right, and the idea was totally legitimate. It's just they started in a more not the simplest case, because ADS-CFT and putting theory in a box simplifies things. Now, in fact, if you think about it, when we say, well, what is the flat space holography? Like, what exactly do we want to say? Because imagine we start with ADS-CFT, and here we write a S-matrix theory. In fact, there is as I'll try to argue a little bit, there is a set of axioms. Well, here these are CFT axioms, but here there are also a set of natural axioms that we will discuss, which are basically analyticity, unitarity, and crossing. So let's say consider this as axioms. Then you just list down all the tools. You have multi-particle states, which are complicated multi-particle states. This was one of the stumbling blocks. You have multi-twist operators here, and in fact, they're as poorly understood as multi-particle states. So, and then you go inversion formulas, dispersion relations. It's just all identical. So why wouldn't we say that, okay, well, we're done. We have flat space holography here. I give you the list of axioms. If you solve them and they look like gravity, it talks like gravity. Yeah, that's it. That's gravity. That's your quantum mechanical theory, which does the job. Well, the crucial difference between these two programs and why people would say that ADS-CFT is a great success, but maybe S-matrix theory has failed, or what has failed to communicate its successes, is that in ADS-CFT, after we formulated this set of axioms and we arrive at this picture, we have a Euclidean formulation of the theory. You can consider Euclidean CFTs, and these CFTs are quantum field theories, which we know, or we believe that they exist. It's not an empty set of axioms. They exist because we have Lagrangian formulations. They exist because we can measure them in the experiment. So we are pretty much convinced that this set of axioms and this set of rules is non-empty, and it's very physical. So until here, everything was the same. But that's the crucial difference between S-matrix theory and ADS-CFT. On the S-matrix theory side, we do not have this. The S-matrix theory, as I try to explain to you, if you let me draw the Penrose diagram of Minkowski space. You have a scattering. You have some particles coming in. If you don't know what this picture means, it just means that particle coming from infinity, scattering, and go to infinity in Minkowski space. This question is intrinsically Lorentzian. So there is no such thing. And moreover, there is no experimental, at least so far, we don't know of an experimental system or lattice formulation such that you can really go and check that it exists. These are the right axioms. They make sense. This is the only thing. I think that's fair to say. But also, I think it's not clear to me that we should expect such simplicity. In fact, I would say that such thing does not exist. The theory is intrinsically Lorentzian. There is no simple Euclidean formulation. And if you try to find one, we'll just not find anything simple. So what do we do then? And I think for many years, the attitude was, well, let's just drop it then.
Sorry, Sasha.
Yeah.
So are you saying that the only way that it is known to formulate the CFT axioms is via analytic continuation from Euclidean, and this is sort of essential to those axioms.
Well, no, I would say.
Why is the Euclidean so important?
Well, Euclidean is important because maybe questions like analyticity, singularities, they're very clear in the Euclidean. You know, the singularities are simple. We have the convergent OPEs, and we can realize the systems in the lab. So it is just in it's a very controllable setting. I don't say that it's fundamental, but it's just a very nice tool which is not available there. In particular, in all these discussions, when we talk, so in these principles, the key one, as we will discuss, is this one. And analyticity is something which people never fully understood, and this is a Lorentzian thing. And we can argue about what are these things. To me, the crucial point is that it maybe okay, not just at Euclidean, but that you know that CFTs exist, or we believe CFTs exist.
But we also believe they exist in Lorentzian signature.
They exist in Lorentzian signatures. They exist in Euclidean signature. They have Lagrangians. Yes, if you try to phase transition second order, you study Euclidean CFTs. There is no analog of this on the S matrix.
But sorry, does there exist some sort of intrinsically Lorentzian formulation of the CFT axioms that could be,
well,
analogous
I guess we have
to
Slava here to comment on that, but I believe that the answer should be yes. It's just Whiteman axioms, maybe plus some OPE. But this should be, I guess we expect it to be equivalent to Euclidean formulations. Yes. So now the second comment. Okay, of course this is not something you can easily go, because okay, let's say we spend our lives studying this set of axioms, and then we learn at the end of our life that the solution to this set of axioms is an empty set. So then it will be a disappointment. However, the thing is that everything that we know from string theory, okay, well, we believe that one solution to these axioms will be, say, or to the S matrix theory is string theory. Everything we know from perturbation theory, from string theory, everything supports a set of axioms. We do not know a counterexample to any of them. And so, okay, either we just forever not do anything about them, or we say, okay, let's just work with them for now and try to derive what are the consequences. And the interesting thing is that, in fact, to do some computations, to do the bootstrap analysis, this is more of a psychological fact. This is like in your brain that what we do is we are totally sure it makes sense. So here, sometimes maybe you have to keep in mind that, okay, maybe there is no S matrix formulation of quantum gravity in flat space. Well, who knows? I don't know, but I believe there is. But if you want to do the computations, then that's it. That's enough. We can just go now, go home and start doing S matrix bootstrap. And in fact, the difference between the 60s and this resurgence of S matrix bootstrap a few years ago, in my opinion, that's exactly what people did. They say, okay, well, let's just drop this. Let's just accept that this is a set of axioms and try to see what we get. Like, what are the consequences? And the remarkable thing, which is really hard to believe, that even the simplest questions, you take the amplitude and you ask, like, what is the consequence of unitarity and crossing together with effective field theory? It was not worked out until last year. So this paper, I guess, there was a series of papers, this IPhT-TV, et cetera. This just happened in 2020. It's really hard to believe. So such basic questions were not asked. But more generally, sorry, it's a long introduction, but I just thought it's an old subject. Shot is looking at his clock, so I'm almost done. Well, so the main message is then that if we accept these things, why is it exciting? Well, because you take what we know. Let's say we say standard model plus GR And then, because it becomes more and more expensive to build bigger colliders, so then we as a theorist can ask, okay, let's combine this with basic principles. And by basic principles, I mean what is listed here. And we ask, what are the consequences? Because, well, this sounds like a question that theorists can ask and should ask. And this hasn't been done. So really, I don't know why, but this hasn't been done. So, and it's, of course, it's more exciting because we do not live in ADS, we live in DS, but let's say we drop cosmological constant because it's very small. So it's with very good precision described by S-matrix theory. And say the paper from yesterday, which was called reverse bootstrapping, was exactly asking this kind of question. Well, we know something from IR, this is something that we know. So this is from, we know from the experiment. What can we say about the UV? And well, maybe we can derive string theory or whatever, but I think this is, at least to me, this is the main motivation to work on the subject, because we will not have experiments which will work at the Planck scale. We will not be able to prove swampland conjectures. So if we are really agnostic, what we should be able to do is that we identify the basic principle and we should work hard to establish that they're true and that we are not fooling ourselves. But so far, everything we know from string theory, from quantum field theory, and from taking the flat space limit of ADS-CFT, we never found any violation of this basic set of axioms. So let's just take them for granted now. And then we can try to derive some interesting physics. So that's an exciting question, and not much has been done for some reason. So that's what I would say is a status of the S-matrix bootstrap today, non-perturbative S-matrix bootstrap. So, and here you can use perturbation theory, experiments, everything that we know from, say, 1, to put it in here. And here we use the basic non-perturbative principles. And then the question, the task for everyone, combine them. Build an object which satisfies both and tell what is the set of possibilities. Is it just a string theory? Is it something else? What are the principles? So that's the basic game we would like to play. Now, since this is a course, or these lectures are not about the perturbation theory of Feynman diagrams, I will not be talking about this, but I will try to discuss the basic principles, why we believe they make sense, what are they, and again, what is a set of tools to make progress. I don't want to, this course, even though this is an interesting subject, so if you take any of the topic here in the 60s, there are volumes written on it with interesting proofs, and I think if someone is eager to revisit them and explain them and improve them, this would be fantastic. But this is not what I'm going to do. I will be sort of very practical and focus on things which you can take and do something with them, and the things which I believe are correct, and I think we have good evidence that they are correct. And so this is the basic setting for these lectures and my take on the S-matrix theory. So, and I chose a couple of quotes in the introduction and the notes. One is from André Martin, who wrote, "One is never sure to have completely exploited the axioms of QFT." And this is, refers to this bootstrappiness of relativistic quantum field theories, that the set of basic principles is so rigid that you're never sure that have we really extracted all the interesting things or not? And I think he was not sure 60 years ago, and we are not sure today. And the second quote was that in this famous book by the Cambridge group on the analytic S matrix, they wrote that we shall be content with plausibility arguments. And so this is a statement that for these lectures, I will not be trying to be super rigorous and really referring to theorems. I try to insert, to put the references in the notes for those who really would like to go as rigorous as possible, but I will not go through proofs and details. If you're disappointed about that, I'm sorry. Now, this is all I wanted to say on general philosophy. I hope it's clear, so please ask questions.
So naively, you might think like you should just be able to start from the CFT axioms for boundary correlators in ADS and just take a flat space limit and derive some axioms for the S matrix.
Yeah, so this is a good idea. Many people have tried and perished on the way. So the reason is that let's say you want to do it. What do? Well, you have your scattering process, and let's say they collapse inside the ADS. Yeah, first of all, maybe it's possible. I don't know, but I'm just now. You have a set of states here in the CFT. Well, if you chop it in half, you have some Hilbert space set of states, which is the same as set of local operators, which you sum over. And this is a unitary theory. Now, as you take the flat space limit, some of the states, they acquire infinite energy. For example, there are large black holes which contribute to this correlator, and they're part of unitarity, but they are not part of the flat space theory. So therefore, when you take a flat space limit, okay, order by order in perturbation theory, sure, you can do it. You will find all the properties, and some people in the audience maybe online worked on that. But the question is not about perturbation theory, really about non-perturbative. And then non-perturbative, it's not clear to me how would you establish the existence of this Hilbert space, which does not contain all the states of CFT. It's kind of some subsector, which does not have large black holes. And then, moreover, in this subsector, you have a non-perturbative unitarity emerging. So you have to control this limit up to e to the minus n corrections. And this just sounds very, very hard to me. So I don't know. Maybe, again, for practical computation, well, if we take the flat space limit and we start with some CFT sum rules, and then we get some flat space sum rules, sure, then we just take it as some IR regulator. And that's what people did practically. But again, in all these cases, as far as I know, it agrees with what you will get if you just follow from here. And moreover, you don't want to follow this procedure. Maybe you want to formulate a set of rules in flat space directly. But I think that it's really not an easy task to going from ADS to ADS CFT to flat space non-perturbatively, and asking questions like non-perturbative unitarity just sounds very hard.
Okay, thanks.
Question there?
But at least when we are talking about massive theories, or just some S matrices which do not involve gravity, then we are more sure about axioms in arithmetic.
Yeah, and we are more sure about axioms, and in this case we are on a firmer footing. Even though, again, say most of these things are sort of well established, but the key point to this whole subject is analyticity, and there is an axiomatic domain of analyticity, and people derive some rigorous bound with it. But I would say this is not. I would like to go more, and it seems like we have much more analyticity, which does not follow from quantum field theory, and moreover, it seems like we can try to work with it and try to make progress in proving this larger analyticity and making progress even for theories with a mass. Okay. But yes, for the massive theories, this is on a, I would say, more firm footing. But again, when I say more firm footing, immediately the questions come up to mind, like how do we prove asymptotic completeness? How do we prove polynomial boundedness? And if you go back to the works of 60s, there is always some long paper by some which involves a lot of formal manipulation, which hopefully does it, but I do not say, if you ask me how to prove it, I would not, unfortunately, be able to reproduce these proofs. So the basic idea is clear. So yes, it is on a firmer footing, but again, say like you recently revisited the relations between, say, CFT axioms and Whiteman axioms, and then you go to Osterweider-Schur, and then there is some assumptions there made, and then why do you accept this assumption? I'm not sure in the S-matrix proofs to what extent we really here anyone understands what is the set of assumptions and set of proofs that are being made. So that would be great to clarify. But yes, it is on. Okay. So it seems like this is clear. So let's just proceed. So the plan of the course of my lectures would be following. I will discuss the. Oh yes, another important point. If you are interested in the subject, that recently there were a lot of lectures about the non-perturbative bootstrap and developments. You should be able to find online. So I also listed the list of people who gave these lectures in the notes. So please check them out. I hope that there will be some complementary material, but there definitely will be overlaps. Yes, so the plan of the course will be the following. So first, I will, as a motivation, and I think because it's useful, I will discuss this toy model for S-matrix, which is known also as a signal model, sometimes it's called. So the idea is that I'll try to, in a simplified setting, illustrate some of these basic principles. Some of them will not be present. So then, hopefully this will be useful. And then we go to the actual, say, relativistic kinematics, whatever, unitarity. Bigger, yes. Relativistic kinematics. Unitarity, something like partial wave expansion. Then we will discuss the really heart of the S matrix is analyticity. And crossing, and here there is a story about axiomatic analyticity domain, Landau equations, maximal analyticity, and this is really the stumbling block of many of the developments, or some important ingredient. Then we'll discuss dispersion relations, which is one of the tools. So I told you this is the basic principles. Now we start discussing the tools to use them. So this is dispersion relations. So here we can derive bound on chaos. We discuss superconvergence and null constraints. And then I would like to discuss some non-perturbative analytic bootstrap tools. and this is this Froissart-Gribov formula. Well, Axe theorem, and what's known as a dragged, the name, bootstrap. And then finally we can hopefully discuss non-perturbative, numerical, bootstrap. And here I would like to talk about, say, fixed point methods, fixed point, primal, and dual. So given my pace, I don't know how far we go. We will be able to go, but that's a plan. So again, here, coming back to this key equation, this will supposed to illustrate the basic principles. And these are the tools. Okay, any questions? Okay, no questions, very good. I forgot to take my clock. What time is it now? Okay, very good. Very good, thanks. So the first topic will be the toy model, where we'll try to introduce the basic principles, and I'll try to relate it to some of the recent developments. By recent, I mean really this year, maybe even unpublished, but essentially sort of essentially understood. Okay, so as I just erased this picture in the S-matrix theory, we ask this question about scattering. And the toy model, we can consider a simpler situation where we have some black box. And this is essentially what S-matrix is. It's some black box which encodes the emergence of space-time and all the dynamics. And then we have some incoming signal. Let's think for now this being as a function of time. So it's some incoming signal. You send it through this box, and you get the outgoing signal. Now, the idea is that, as I told you, that the S-matrix operator, it allows you, given the incoming signal, to predict what is the outgoing signal. So in the context of relativistic scattering, you start with the particles, and then S-matrix tells you what is the state of particles and the outgoing state of particles after the time evolution. So this is the time evolution. This is the whole space-time. But for this model, we can take this f out t to be integral s t minus t prime f in t prime. So here I postulated, and we'll proceed with that if you give an incoming signal, then there is this operator. I would like it to be translation invariant, so it depends on the indifference of times, which allows you to compute the outgoing signal. Now, you can in practice think of this as, let's say you have a particle and there is a background of other particles which serves as a medium, and you send your signal through this medium and you get some outgoing signal. Now, switching to doing the Fourier transform of this equation, you can rewrite the same formula as a famous fact that if you have a convolution in coordinate space, you will get a product in Fourier space. So you get this relation. That's just a Fourier transform of this. And the definition, so let me write my convention for the Fourier transform. So I'll write this S of t is equal to now. Let's introduce the first concept, which we also know exists in space-time, and it's a really crucial fact about say Minkowski space, the concept of causality. And the causality states in this model is a very intuitive thing. Let's say you have the incoming signal to be 0 for t less than 0. Then the causality tells you that the outgoing signal has to be also 0 for t negative. So in other words, this box does not create, it can only respond in a way which has which does not create signal where it was not there. So if you have that signal was 0, you have it 0 outgoing as well. And of course, in relativistic theory, this will be the story about the light cone, and we will discuss what it is. Yeah.
Sorry. Yeah. Is it obvious that the outgoing signal should be linear in the incoming signal in that way? Like, is this an extra assumption, or
it's a model? Yes.
Okay.
So this is something which is yes, makes sense in maybe in the weakly coupled theory and to some leading order, but in a relativistic theory, it's not obvious. No.
Mm-hmm. Oh, thank you.
Now, well, let's look at this equation. Now, if we want to impose this condition here, and at the level of this equation, in fact we discover that. Let me write that this response has only non-trivial support for theta minus theta prime. So if it's 0, then it guarantees that the outgoing signal will be also 0. So therefore, if you write the Fourier transform 0 to infinity dt, which is inverse of this, we have the following formula, and the key point here that the integral now goes from 0. So this is an expression of causality. And now you see that if we have such an integral, then we can deform it in the upper half plane. So if we try to deform omega, if we add to omega some imaginary part to move it in the upper half plane, so omega going to omega plus I gamma, oh, I'm sorry, I gamma, then this exponent acquires a damping factor, which is e to the minus gamma t. So in fact, it can only improve the convergence of the integral, and therefore we conclude that in fact this this S matrix which we discuss in this model, thanks to causality, we can continue it in upper half plane, and it's analytic in upper half plane. So so we see that this is this really basic fact, that the fact that this integral starts from 0 allows you to analytically continue in the upper half plane. So now causality implies analyticity in the upper half plane for this S of omega, and this will be true for all the scattering amplitudes that we encounter. So in particular, also we can define then we can define this, think of this original S matrix. So here omega is real. Let's say we consider here omega is just the real frequency as a limit from the upper half plane, where the S matrix is analytic, and this is what is sometimes called I epsilon prescription. So the scattering amplitudes scattering amplitudes that we will be discussing, they will be can be obtained as some boundary value of an analytic functions, at least for the cases that I will be discussing. There are always subtleties. Okay, this is, but essentially this is a basic point. And so here, this illustrates this key connection. When we talk about basic principles of the S matrix theory, you see that causality implies analyticity. So in fact we will be dealing with analytic functions of momenta of the particles, which was analogous to this omega, and then the one of the key questions is what is the domain of analyticity? Can we extend it, etc., etc.? But the basic point is simply this. And second is you can ask, okay, can you go in the other direction by, let's say you start with something which is analytic in upper half plane. Can you show that it's causal? And the answer to this is no. And to see it, just consider the following example. Take S of omega to be e to the I omega capital N. So this is, let's say n is an integer. And then let's say we take n equals 1. Then if we continue omega to the upper half plane, then it is indeed, you can check that this is a causal S matrix as long as C is positive. So this you can do the exercise. This is of course the all analytic in upper half plane, but this will be analytic in upper half plane as long as this will be a causal thing as long as C is positive, and by coincidence this is what gravity gives you. So in fact this is a gravitational case, and if you compute the effect of this box, what does it do to signals? It leads to delay of signals, and this effect is known as Shapiro time delay. Now, on the other hand, if you consider higher n's, and again, well, you can consider an example something like this, e to the I omega cube, and you can just check using this formula, and then Fourier transforming back, that this S matrix is not causal. So in fact, analyticity in the upper half plane is necessary, but it's not sufficient. So what are the extra conditions that you need? Monica, you since you know better, shall we take a break at some point, or? Okay, I will take a break soon. So this you can check that, let me write it so that there is no confusion. Check that it is not causal. Now, the reason for this you can understand. How do we conclude that something is causal, given that S of omega is analytic in upper half plane? So look at this formula. Let's say we want to show that that this S of t does not have support for t less than 0. So we want to show that S of t is 0 for t negative. So how do we do that? Well, let's imagine that t is negative in this formula, and let's try to deform this contour in the upper half plane. Well, if you deform this contour in the upper half plane, this omega contour, and we can do it because we agreed that causality, when we talk about causal S matrices, is analytic. You will see that this exponent, it acquires, so if again we do this, shift omega goes to omega plus I gamma, this guy acquires this factor, and here I use that t is negative. So it's damped, and if S matrix, if this S of omega does not grow too fast, then you can just deform the contour in upper half plane and you get 0. So you deform it for large gamma, it becomes damped, and that's it. However, you see that to do that, you have to make sure that S of omega does not grow too fast. Because you see that here you have I omega cube, and in fact you will find that this factor blows up very quickly in the upper half plane. You cannot deform the contour, and the argument does not go through. Therefore, we see that there is a bound to run this argument. We want to say that the S metric should grow slower than this exponential, say, in the upper half plane. So if we find that the S matrix grows sub-exponentially in the upper half plane, so if there is some constant which bounds it, sorry? White is better. Sorry. Okay. I somehow switched to blue. So if S plus I gamma is sub-exponential, in gamma, and gamma is positive, then we can run the argument, we can close the contour, and we get causality. So to go backwards here, we need to add plus sub-exponential growth. Now, here again, these two ideas that first of all, yes, you can often encounter these words that the scattering amplitudes are polynomially bounded, functions of momenta or equivalently omega. So by this, usually what is meant is something even stronger than that. Of course, if you have, say, you take omega, the absolute value of omega to be large, and you take something like this, this is sub-exponential, right? It's a polynomially bounded. However, this does not follow from causality only even in the signal model, and it's true for relativistic amplitudes as well. When people prove this, and I think it would be great if again someone revisits this proof, because there are two proofs for this property for relativistic scattering amplitudes. One is relied on Whiteman axioms, and another relied on this Araki-Hag axioms for algebras in the regions, and they both claim to derive this, but somehow yeah, it's not, at least I do not have a clear picture in mind what exactly is done in these papers. Now, in both cases, well, when you derive it from Whiteman axiom, you use the fact that Whiteman axiom, you assume that Whiteman functions on tempered distributions and they're polynomially bounded. So it follows from that there. In Araki-Hag, or Hag-Kessler maybe is the right one. I'm not sure where it comes from, but in many cases, in fact, in all cases, which we'll find both in quantum field theory and in gravity, these kind of conditions are true. However, they come if you add to causality unitarity. So, yeah. Yes, this is in the upper half plane where it's analytic function, it can be pointwise true. On the real axis, it's true in average sense, yeah. Now, so this polynomial boundedness comes from the extra assumption of unitarity. It comes also in the all S matrix proofs. And this function of n, it will depend on the theory. In realistic cases, mass gap or not mass gap, can depend on number of dimensions, space-time dimensions. But in the end, we always seem to land on this condition. So,
sorry, Sasha.
Yeah.
Aren't you also assuming locality of the theory? Like, can't I have non-local unitary theories that may be full of slower?
So yes, that's an interesting question. Where are there theories for which this is not true? And presumably you can cook up a gadget
I'm not sure I'm saying something, but for example, if you take non-commutative super young means,
Yes.
doesn't that thing have some sort of exponential behavior? I don't know if it's highly damped or maybe it's highly damped. At infinity, and I'm surprised that you're saying that you're only using causality and unitarity, but don't make any mention of.
Well, I'm using causality for the. Okay, I will have to this. Maybe I'll have some comments, and let me mark that we discuss this point as well, because I think it's relevant. And maybe now we can take a break. Yeah. First correction to the first lecture is that Slava pointed out that in fact in this old papers, I told you that it has been shown that from the Whiteman axioms you can have this polynomial boundedness. In fact, there is an extra assumption that you have to assume that LSZ or the time-ordered correlation functions are also tempered distributions, and this hasn't been proven. Okay, so that's something maybe you want to keep in mind. Now, the end we ended with a statement of sub-exponential growth, and I told you that in fact we will see polynomial boundedness coming out from. So let's say you establish the polynomial boundedness from some other reason. You can sometimes improve it, or you can even establish it using unitarity. And again, this is a very general.
Sasha?
I'm violating, right?
You are, but also I have a question.
Right.
I mean, you didn't really justify how much the signal model is supposed to capture about Gerasimetry either. So
we're coming to that,
you know.
But I'm telling you that in fact it does. So I'm saying you that all these things that I told you are true for the amplitudes. I haven't derived them for you, but
right. I see. So even the naive exponential growth that seems to be allowed before you impose anything else, that gets cut down too.
Yes.
Okay. Thanks.
Yeah. But no, you're right that I haven't showed it. I haven't showed it for the amplitudes. But I will discuss unitarity now, and then I will discuss the relation to relativistic scattering in next, because I think Monica's question also was about that. Okay, unitarity in general expresses the fact that the S matrix is supposed to describe the time evolution in quantum theory. And therefore, if we start with some quantum state, let's say we start with a pure quantum state, and it has some norm, and then we time evolve using the S matrix, the time evolution should be unitary. That's what we expect. In the context of sigma model, the formulation of unitarity will be the following. I take the L2 norm of the signal, which is defined like this. So here I'm just telling you, I'm postulating. And you take the absolute value square, and this should be less or equal than the norm of the incoming signal. So again, the idea is that well, you might create some other particles during the process of doing that, and but you cannot change the norm of the state. And here, effectively, this norm will be related to some notion of a norm in quantum theory. But let's just proceed with that. Now, the claim is that if you have this property, then you can prove that S of omega is less or equal than 1 in the upper half plane. So this property is the same as we finished on that board with n equals to 0. Remember, there was omega to the n. Now we show that n is equals to 0. Now let's just quickly prove it. And the proof is like that. Let's take an ingoing signal to be like this in a frequency space. So we say pick it around some, just a pole in some complex in the lower half plane. And in the coordinate space, it is an exponential. It is a function which starts at 0. It has a phase omega 0 t, and it has square root 2 gamma. So this is just a choice. I'm now choosing a certain ingoing signal, and now we consider the following set of inequalities. Consider the norm of an outgoing signal in a frequency space. And so this is, in a causal model, is given by this. Here I use the fact that it starts from 0. Now if we think of this as a scalar product, we can use Cauchy-Schwarz inequality and bound it. I think I'm doing exactly the opposite of what Monica asked me to do. Okay. Yeah, I will. Okay. Well, but now it's already filled, so I will naturally shift. And so I hope this is clear. So this, we think of this as a scalar product. So now we have and we would like to bound this, and this, of course, is just a norm. So this is f out, and this is equal to 1 over 2 im of omega. So the punch line, and you can check that for this choice of a signal, we just chose it like this, that you can check that its norm is just 1. So, and now we use unitarity to bound therefore f out also by 1. So therefore the result is that we just showed for this case that twice omega. Now we have, let's try to bound the S matrix. And this is using this inequality. Is this. And finally, what we do is that, okay, we can take this formula for f in of omega, and we evaluate this at omega 0 plus I gamma. So then you see, if you do it, you get that this guy is 1 over square root of 2 gamma. And so we taking it square, we get 2 gamma in the denominator, in the numerator, and this is also gamma. So we get that less or equals than 1. There is some water here. It melted. Okay, I'll have to deal with that. Yeah. But maybe I should use this thing. So yeah. So we derived this for this signal at this point, but now we can choose any point, and we get that it's bounded in upper half plane. Now, an important case for, again, before we go to the questions of Eric and Monica, which are very important. So as an exercise, or you can consider the following: S of omega. Imagine that you have a theory where it takes a form omega to some power p plus c plus some maybe order of c squared, and c is very small. So it's some kind of perturbative expansion where S of omega takes this form. And now the exercise, you want to impose that this guy is less or equals than 1 in upper half plane. And you need to check, you can show that, say, this can only hold if p or less or equals than 1. And this is known as a bound on chaos. Well, type of. And when p is equal to 1, which is maximal power, c has to be positive. This is the statement of the Shapiro delay we discussed. Now, what is the relation? Okay, so here what we achieved so far, well, it follows from this. If you take this model, try to go to an upper half plane, you will see that it violates this if this is. S omega is equal 1 plus IC omega to the power p plus some c squared, which we can drop. This is for any omega. Well, there is a region in the omega plane for any. I mean, it's a true statement in a complex plane. Now let's assume there is a chunk of complex plane where this is true, and this you can drop. Can you repeat the question? Slava is asking, I don't see how what you claim follows from what you said. So, okay. Shall we can do it right now here, and the basic idea is, let's say we take again this example, 1 plus I, say, so we want to impose that if we take 1 plus I c omega p, and here we take, say, omega 0 plus I gamma e square less than 1, and now we do it to order linear in C, and so we just write it as a, this equation. This inequality is true in upper half plane. That's for sure. Now, yes, I assume that it's true in some region omega, in some region which I do not specify, but I think it should be enough as long as we have a piece of this upper half plane with some finite range in omega. I thought this should be enough without saying too much about lambda. But okay, well, let's check that and see what follows from that. But yes, the assumption here is that this is, I give you an S matrix. We believe that it works somewhere in this chunk. We can even assume maybe some strip, so it holds somewhere here. This is, say, in relativistic, in realistic scattering, maybe this is more reasonable. And I thought that even, in fact, that the fact that it holds somewhere here close to real axis will be enough, because what we will do is we just take this function. So to the order, let me take, say, for simplicity, this sort of function. So to the leading order, we have it's purely real. So this matrix, this is purely imaginary on the real axis. As we go in the upper half plane, the leading correction to 1 comes from the imaginary part, and then we just see how this imaginary part behaves in this strip. And if you have a p larger than 1, we will find the direction in which it will be growing, and that should establish the claim. But I think it's a good exercise to do that.
No, but in fact, Sasha, now I can see that it has a chance to work. So
okay.
Well, before I was totally blocked. Thank you.
Sorry, Sasha, just to make sure I'm following. So if you're doing wave functions rather than signals, then
okay, let's go to that.
Then, sorry, S mod S squared would be 1, but only on the real axis. Is that the point? And now if you try to extend it to the upper half plane, then you have an inequality? Is that the point?
Let's discuss the real case. I think it's time now. It's time to go from this to relativistic scattering. And the relation to the actual relativistic scattering is not obvious. So, and there were two approaches. I think there are kind of two approaches that one can discuss. One is the approach that uses coherent states, and this was discussed in this paper by by Kamani et al. About the 3-point corrections to gravity. There is this appendix there. But I think here I will not go over these details. Well, I can say you the basic idea. The basic idea in the relativistic scatterings, you have light cone coordinate u and v. You think of the particle coming. So this is a really important. It's light cone coordinates. So the coordinate v is what is t in the signal model. So it's not time. It's important that because now we can imagine having some causality formulation in the light cone if you have a signal coming, and now there is some medium created, for example, by some other particles. So let's say you have some other particle here, and as your particle comes in, and because this is a light cone, you want to impose that it does not come out here. Now, and this is, of course, relativistic causality because, okay, these are space-like separated points, so you want it to come after. But the immediate problem that you run into this when you try to come to the relativistic model is that here we always worked for all omegas. So for all omegas, we had these nice pictures with signals. Now, if you go relativistic, there are two problems. One is that if you have a particle, if you have an actual particle, its energy can be only non-negative. That's a one thing. And the second, in fact, if you want to think of this scattering process, it's it only makes sense if these particles are moving with some, with big, high energies, so it makes sense to discuss it only in a sub-region of the omega plane. So it's only makes sense in some sub-region, and then it's not might be not completely clear how to generalize, how to really run this argument. And so in this paper, the approach was taken as to think about some coherent states in a space of fields, where you take some states which are formed by some asymptotic field dt, and then so here now you can take any f in. It's a quantum field. It acts on the vacuum, and then you try to run the argument, but then well, then you see that it's related to the signal model, but then the relation is not to the 2-to-2 amplitude is not completely clear, but the idea is that if you use these coherent states, that then at least in some subregion here, these coherent states correctly capture the 2-to-2 scattering amplitude, and then this bound holds. However, this is not super clean argument, but this is what was presented in that paper. Now, what I would like to discuss is, let's try to make it a clean argument. In other words, what can we turn this argument into a statement about the 2-to-2 scattering, really? Now, so yes, the question is, can we go from this toy model to say 2-to-2 relativistic scattering? And here, something which is crucial, and this is a property of relativistic theory, is the following: that yes, this we discussed in the signal model the properties of analyticity and the properties of unitarity. Now, both of these things they do apply to 2-to-2 scattering amplitude directly. However, what hits you when you try to generalize argument, this condition, that let's say we consider literally this model. We think of the medium as created by this particle. And so we consider now 2-to-2 scattering, these two particles going into two other particles. Let's consider the scattering in the impact parameter space. So you imagine, say, two-wave packets separated by some distance. There is this guy, and there is this guy. Oh. There is some impact parameter B. And there is some center of mass energy S, which you can, little s, which you can think of the product of omega from the signal model times, say, omega prime, which you can think of the fixed energy of this particle. Now, what happens is the following. If you look at the complex plane, omega plane, and here I will be now connecting to the toy model that we discussed. If you look at the now S matrix scattering, the actual 2-to-2 relativistic scattering as a function of this S, which is linearly related to omega, and B, you find the following picture. And this should be true both in gravity and in QFT. Let me call it still omega to connect to the toy model, but just keep in mind that then omega will become S very soon. So what you will find is that this S of omega in B, it is analytic in upper half plane. This checks. This we have proven. Moreover, you see that there is some branch cut. Doesn't matter, but there is a branch cut for positive omega effectively. So let's start it at 0. Or it can be, since particle relativistic, it has minimal energy for say some m. But it's true that you find that on the right cut there is a statement of unitarity, which says exactly this. We haven't discussed it yet. We will come to this shortly, but you can show this, the case. And so, okay, now you feel, okay, what if you want to, you have analyticity and we have half of unitarity. But of course, to run the argument, you say you want to use some kind of maximum principle of the complex function. So if it's analytic and it's bounded, say polynomially bounded in the upper half plane, and you want to bound it by 1 in the upper half plane, you have to bound it on the boundary of the region of analyticity. And there is this left cut. So there is this omega negative. And what happens in the relativistic theory that, yes, at positive omega, it does look like a signal model, but for negative omega, and this is related to the property of crossing, you instead describe a different physical process. Because it's a relativistic theory, we will see that what happens is that you start describing something slightly different, and in fact, there is no bound on this cut. It's just not bounded. So at the level of 2-to-2 amplitude, at scattering at some impact parameter B, the problem is then to bound this thing on the left cut, because if you manage to say that it's bounded by 1, then you show that it's analytic and it's bounded by 1, then it's bounded by 1 in the upper half plane. However, this hasn't been done yet. However, there is a way to solve this problem indirectly. And this is what this latest development in the S-matrix bootstrap during last year were about. And the way you do it is that you can derive this sort of bounds by first going to the momentum space. Then we will have to understand what crossing is. We will first impose crossing carefully and unitarity, and then we will go back to the impact parameter space, and then we will start getting bounds like that. So yes, the relation to the relativistic scattering is non-trivial, but the claim is that, okay, either you work with these coherent states, or you have to address the left cut. And so until like a year ago, this was the only argument that we knew of. But then you start, there are many subtle things, and then you have to assume, okay, when does it exactly apply? It has to be weakly coupled, say, theory. But now I think we have a technology to kind of upgrade this signal model to 2-to-2 scattering, but it goes through this latest developments, which I will hopefully be able to cover. So this is one comment. I don't know, Eric, if it has anything to do with your question. Yeah, so the basic
It does.
I think the basic point and the true difference between signal model and relativistic scattering in the context of 2-to-2 is a property on the left cut, which for the signal model there is no difference between positive and negative omega, but for 2-to-2 particles we will see that positive and different energies really different. So this can describe say ingoing particles, and the negative omega will describe outgoing antiparticle. And then you want to bound this guy on the left cut, and in fact you sort of can do that, but it goes through an extra layer of technology where you make this you really make use of the crossing, and that's why it was hard to upgrade it, and it was only done recently. So that's my basic comment. Now I have two other comments, and this is related to what Monica asked me before. So let me make these comments. One thing you could have object right away is that, okay, well, I use in my argument I use some signals which are sharply localized. I take an ingoing signal which is exactly 0, say before some time. However, we know that you have a relativistic particle. It's not something that you can easily localize. If you try to localize a particle sharply, you create more particles. That's an unfortunate fact. So how does it all, any of this make sense? And how do we then formulate causality in relativistic theory? Like, what are the implications of causality exactly? And there are two answers to these questions that have been given in the past, and I think the implications of neither is fully understood. At least that's my impression. So one answer to this question is the following, that we can introduce a notion in relativistic theory, we can introduce a notion of microcausality. And this is something which you can only do in quantum field theory. You cannot do it in gravity, because this relies on the fact that in quantum field theory we have local operators, and local operators commute at space-like separated points. And so this is pretty sharp. Now, of course, this is a statement about the operators, but operators, not about the particles. So you can suspect that going from this to, from statement that this commutator is 0 to some statement about scattering amplitudes is not a trivial step, and indeed it's not. In fact, if you want to make this step, it requires so first the LSC procedure, which is the reduction formulas, which allows you to, by putting these operators effectively on shell, to read off the amplitude from the correlator. So there is an LSZ involved. And the second thing is that you have to, it's necessary to go through the steps of analytic completions. In other words, if you use this, if you use if you take this commutator and you say impose it into some other state and consider the analytic properties of this object based on simply the fact that you say your theory is gapped and that it's causal, you derive a certain domain of analyticity, which is called the primitive domain. And then the statement is that the intersection of this primitive domain with the on shell is empty. So you have to actually, you first establish some analyticity domain. Then you, because you are dealing with functions of two variables, effectively S and B or S and T, there are some general theorems that if you have a certain analyticity domain, a function of two variables, you can often extend it. And so after you extend it, then you find that it intersects with an on shell, and then you derive some properties. So this is one approach, and this is what has been done in the axiomatic quantum field theory approach to derive analyticity. And there was a second approach taking, which is known as a macro causality. And this is something more subtle because you formulate it in terms of the, and yes, I added a reference to my notes, the paper which I know they discuss it best. But the basic idea is that you start considering effectively, okay, because it's a relativistic particle, so it's not, we do not have a Schrodinger picture where we take a square of the phi and we say, okay, the particle is localized there, but we can take, I don't know, the expectation value maybe of stress tensor or introduce some sort of measure of localization and then identify the regions where the sort of most of the particle is carried and regions where it's exponentially suppressed. So in this way, we sort of asymptotically, at least in the asymptotic region of space-time, can localize the particles. And then the basic idea is that the transfer of information or transfer of energy momentum on macroscopic distances. So if you want to send a signal, effectively, if you want to send a signal from here to nearby galaxy, it should be carried, the fastest you can carry is by on-shell particles. So this is vague. I think this is vague partially because I do not understand very well this subject. So it would be, but the basic idea is that you then postulate that if you have a, say, a scattering process and you take your wave packets and you displace them in such a way that there is no way that they can carry information by on-shell particles, so it's just don't overlap, then the probability of this process should go exponentially to 0. And then there is a mathematical technology that turns the statements into analytic properties of scattering amplitudes, but what you get is weaker. So what you get from quantum field theory. So the advantage is, of course, because it's formulated in terms of particles, you can apply it to QFT plus gravity in principle. But the truth is that I don't know if a single paper which discusses macro causality for massless particles. As far as I know, this is an open problem to formulate. What do we mean by macroscopic or asymptotic causality exactly for theories with massless particles? It would be very interesting to formulate it and to derive the analytic properties. So this approach for macrocausality was been done for QFT, and I have a reference in my notes for the paper which discusses, I think, the state, more or less state of the art for the QFT, but they do not say a word for gravity. Well, from the signal model, we have some intuition what it means. Maybe in the end, I suspect that in the end, whatever this notion is, we will rederive again the same things that we were discussing: analyticity in the upper half plane, polynomial boundedness, etc., etc., etc. So, but I just wanted to mention that. So this is yes, and now coming back to the question by Monica, she asked, what about some non-commutative theories? Well, I know nothing about it, but if you have a way to relax these conditions, if you have some fundamental length, so that this equation does not make sense, then what I said does not make sense for. Now, again, if you want to relax this, not sure what would it mean, but precisely at the level of the scattering amplitude. So having an exponential is not a problem per se, because we have exponential in gravity, but it's an exponential which decays. Now, I don't know of a single example where things grow in the upper half plane, and there should be some violation of causality which comes with that. So yeah, I don't know such examples.
Yeah, I think in analyticity they might
Mm-hmm. Okay. Yeah, it's also I don't know. Is there a notion of S matrix there? So yeah, and the momentum is conserved, or because if p mu and p nu do not commute, then we cannot diagonalize them simultaneously, right? But for momenta, it's commutative. Yeah. Okay. Yeah, I don't know what else to add. Okay, this finishes the toy model part. So I will continue with something, maybe the most boring part, which is just relativistic kinematics. Now I can continue with it next time. Yeah. Okay, well, let me, if I can, I will take them. So, okay. I will take 15 minutes. But yes, I will not be able to say much, but I will introduce the basic. No, I am fine. So, for the rest of the...
Can I make a comment about analytic completion?
Sorry?
I wanted to make a comment about
please.
analytic completion. So I think, you know, it's often said that this analytic completion is something mysterious and unphysical. But I think, you know, nobody says that Cauchy formula is mysterious. We know that if we know an analytic function of the boundary of a disk, and there's a Cauchy formula which just tells us what it is inside the disk.
Yeah.
You know, we've seen it many times, so we don't find it mysterious. So I think this analytic completion, it says just that for functions of two complex variables, there are some fancy variants of Cauchy formula, which we are just not familiar with, because, you know, we are only familiar with one-dimensional Cauchy formula. You know, in one variable we know what to do, but in two variables there are some more complicated variants of Cauchy formula.
Yeah.
That's all there is to it. There is really nothing, you know, the moment they have names, these formulas. So the moment you stare at them, they're just explicit formulas which tell you basically that if you know a function on a certain boundary of domain, there is some integral expression that tells you how to compute them inside this boundary. And they just don't follow trivially from Cauchy formula, and so we find them mysterious, but eventually that's what they are. They're just some explicit formulas, integral formulas. So we should just get more familiar with them, and maybe we will not find them so mysterious after we've seen them several times.
I totally agree. So here, this is just a piece of technology, which
very explicit technology. It's not like some abstract theorem which says, you know, it's not a black box. There's just some explicit integral formula behind it, which has a name. I forgot the name.
Yes. No, I didn't want to make an impression that this is a mysterious step.
Yeah.
It is a very explicit step. Yeah. And it's true also that, as you say, and this whole business of scattering amplitudes relies on theories of functions of two complex variables, and there are things. This is a less familiar. This is something much less familiar to many of us. I believe, though, that the one interesting aspect here maybe is that related to that well, we start. I think as matrix theory becomes interesting when it's sort of goes beyond QFT maybe, or you get something a little bit more than you expect. And here, it's interesting that we start with this function of two variables. We derive something from fundamental principles, and then we can go beyond, either using analytic completion, or we can go beyond using, say, unitarity. But as far as I understand, even this problem of just taking this program, okay, for two variables, maybe it was done, and there are explicit formulas. But let's say take 2 to 3 amplitudes. So to work out what is the primitive domain, to work out what is analytic completion, there will be more than 2 variables involved, and I think very little has been done. And I'm not sure if there is a mathematical technology, or to what extent, if we have a like how explicitly can we actually do that, say, for 3 to 3 amplitude, or 2 to 3 amplitude. This I'm not sure. For 2 to 2, yeah, I think, as you said, yes, there are very explicit formulas. Do you know any results for 2 to 3 or 3 to 3 when there are many complex variables?
No, there are similar formulas. They're valid for n complex variables. I think so. There are some formulas which are like analogs of Cauchy formula, and those are very explicit. The problem appears. So there are 2 types of analytic continuation, even for functions of one complex variable. One is like just apply Cauchy formula. Another is when you like have to do expanded Taylor series, then then just keep going, and then maybe you will discover that there is some complicated Riemann surface and so on. This problem is non-trivial even for one complex variable. You start from some function in a disk, then you start extending it analytically. You don't know where it will arrive. Very non-trivial. What kind of Riemann surface you will discover. So that part of the problem becomes, for several complex variables, even more non-trivial, and for this there is no ready-made recipe. But I think what we could hope to like get better intuition is about this analogs of Cauchy formula. That should be relatively trivial.
Okay, thank you, Slava. 10 minutes, right? I still have. So the basic object that we will be considering is again this S matrix will map with state of say n particles, or the state of m particles. So the basic notion of the of this object is the fact that asymptotic states come are just states of free field particles, and the intuition is that as particles propagate far apart, they stop interacting and they become effectively free. Now this is trivial this is very intuitive for gap theories. This still kind of makes sense for massless particles as well, because the interaction still dies off, and this is hard to make sense of in 4 dimensions in gravity. So that's famously the problem of infrared divergences in 4D gravity or electrodynamics to that extent, where I think it's essentially an open, at least I haven't seen it's an open problem how to really apply this technology whenever there are infrared divergences, and I think it would be great if we have the analogs of things which I'm telling you about for this case, but this hasn't been done. Now the particles are famously labeled by unitary reducible representation of the Lorentz group, which is, so for us in D dimensions, we imagine that we have something like this, either asymptotically or exactly. And so then I will be talking about massive particles, and well, the massive particles will be labeled by their invariant mass, which is just the square of their Lorentzian momentum. And as we already talked, they have a positive energy. And also they are labeled by spin, which is how they transform under the rotations of the little group. Now, for the purpose of this lectures, most of the time I will be talking about scalar particles, so they will not have any spinning degrees of freedom, so they will be just labeled by their on-shell momenta. So this is the on-shell condition. So effectively, they're labeled by their mass and their d spatial momentum. Now, we assume that the theory has a Poincaré invariant vacuum, so it's invariant this plus translation, and the Lorentz group plus translations. And then to describe the Hilbert space of this interacting theory, we simply introduce the creation and annihilation operators, because the theory is free, and so let me write it. So for scalar particles, it's P naught, d minus 1, p minus q. Then the one particle state is defined simply by acting with this creation operator on the vacuum. And so we can define the one particle Hilbert space as a space of square integrable functions restricted to the mass shell, in particular because we can take superpositions of such states. So we can define the norm on the space, which is d mu 1 e. So we have dagger. Let me just be right in terms of d-dimensional momentum to p, and the measure 1 refers to one particle is this 1 over 2 pi d minus 1 theta p naught delta p square plus m square ddp. Now, if we have a theory of a single particle, single scalar particle, so let's say these are all identical particles, we can define, of course, also the n-particle Hilbert space, which is just a symmetrized product because they satisfy the Bose statistics of one particle state to the n. So and then the complete Hilbert space of the theory, if it's a single scalar particle, will be just a direct sum of all this n-particle Hilbert space from 1 to infinity. And in particular, the important formula for me from this will be that we can resolve the identity, and this will be the basis for the for unitarity. It's this our vacuum plus some from n equals to 1 to infinity integral the measure on the d mu n p of p1 n p1 pn, and the measure is on the space of on-shell momenta is 1 over n factorial, coming from the fact that the particles are identical. And product d pi 2 pi t minus 1, and we put that energy of the particle is positive, and we put every particle on shell. And now let me just write the final formulas, a few of them. So the S matrix will be this gadget, which maps for us, if we take some in state of multi-particles, it maps it to the, say, to the outer state, which is given by this matrix acting on psi in. And because it's we want to think of this as some quantum state, and we believe that this is a time evolution, so we wanted to preserve the norm of the state. So we have the norm of the out state is equal to the norm of the in state, and as a result, the S matrix is an operator that preserves the norm, and I guess we want it to be linear also, so we have that it satisfies the unitarity. So this is a unitarity condition for the S matrix, and then where this 1 is this thing. Now, well, I will proceed with discussing the few basic properties of this S matrix, but probably I should just stop for today. Well, you know, 5 minutes and 5 minutes. So, okay. Yeah, maybe then, yeah. We have to go for lunch, or you're just leaving now?
Okay, so let's all thank Sasha for. So, any questions? Also, the online can ask questions if. Microphone, please.
So, is there anything interesting to say about the fact that you are assuming that the full Hilbert space is generated by just putting particles together, that somehow that there's no leakage, that whatever escapes to infinity somehow is a particle. Well, I guess it's very natural. So, is there anything interesting to say about it?
Yeah, it's. I suspect there is something interesting to be said about it, but I will not be able to say it. No, I think it's, as you said, it's natural. However, there are situations where it is not natural. And then, say, if you try to define theory like this with infrared divergences, it just does not make sense.
Yeah.
So, okay, since it breaks down here, so there is definitely a failure mode, but well, this failure mode is this long-range interactions, and I think there is definitely something interesting to be said about how do we write. For example, just even the simple question. Let's say we take QED and consider, so it has charged electrons. Well, and gravity, of course, does this formula really make sense? Because, well, if we consider transition amplitudes between, say, a finite number of particles, they're all infrared divergent. So if there are charged, okay, so 2 photons into 2 photons is infrared finite, but if we have, say, electron-electron scattering, then we need to consider inclusive observables to get some finite results. So if I just consider some transition with a fixed number of photons, it does not make sense. Well, we understand that maybe it's related to the fact that we do not impose correctly Gauss law. So then we can introduce Faddeev-Coolidge states to impose the Gauss law. But however, no one has written a formula like this for Faddeev-Coolidge states. So what is the resolution of identity in the theories with massless particles? Well, there is a simple fact. If we have a oscillator, if we have a bosonic oscillator, we can resolve identity in terms of just the Fock space, or we can resolve it in terms of coherent states. There is a formula for completeness. However, I don't know if it goes through for Faddeev-Coolidge states. For example, is it true that Faddeev-Coolidge states are enough to resolve the identity, or something else is needed? I don't know. I think this is very interesting and very concrete problem to write unitarity relations in terms of some proper states for theories with infrared divergences. And this is related to the question you asked. For massive theories, I guess maybe there are some it will be insightful to understand precisely how it comes about, but it's a bit hard to imagine that there will be any surprises. That's all I can say.
More questions? Actually, I just realized, may I have a question? I don't know if it makes sense. So here you've written a resolution of the unit operator in terms of perturbative states.
These are non-perturbative states.
These are not perturbative
Yeah,
states.
so these are pions. These are really true asymptotic states. So in QCD, this would be pions, say.
And in gravity?
Gravitons. In D larger than 4. So effectively, if you form a black hole evaporates to gravitons, and then you have a free gravitons at infinity.
So it's not a restriction, the fact that you're not allowing black holes in the final state?
No, no. Black holes are not allowed in final states because they decay into gravitons. So here I'm making assumptions that everything decays. Well, if black hole will not decay into graviton, I will not pronounce a black hole a new asymptotic state, and then we will include the sum into this. So everything that does not decay is included in the list of asymptotic states, and it's included in the sum. But whatever does not decay stays there forever and is free, effectively free for the purposes.
Okay.
That's
More questions? Okay, if there are no more questions, let's thank Sasha again.